So hello, everybody. My name is Nikos Kolotouros, and I am a computer science PhD student here at the University of Pennsylvania, advised by Professor Kostas Danielidis. Today, I'll present part of the work I did during my PhD on reconstructing 3D humans from images. So let's start this talk by quickly introducing you to the problem we are trying to solve. Our input is an image of a person, and our goal is to reconstruct a 3D body in the form of a mesh. To represent the body model of a person, we make to represent the 3D body of a person, we make use of body models. So what is a body model? A body model is a mesh representation of the human body equipped with a set of pose parameters theta and shape parameters beta. So given an initial template like the one you see on the left, we can use the shape parameters to alter the body shape. And can you also notice the white dots on the shape? These are the major body joints that define a kinematic chain. We can control the pose of the person by changing the angles of these joints. So some popular examples of body models are Scape, Simple, Adam, and GAM. In its most general case, single image reconstruction is intractable because of the ambiguities. One example is scale depth ambiguities, like the one you see in this picture with the Eiffel Tower. We know that the object shown here is the Eiffel Tower. This means that because it's over 300 meters tall, it has to be very far behind the two people that appear as if they're touching it. If we did not have such knowledge, it would not have been possible to determine where this object is located in the world. It could have been a much smaller object right next to these two people. Ambiguities are not all about scale, though. Here's the popular Ames room illusion. The priors in our brain tell us that we are looking at a typical room layout. We have a floor with checkerboard tiles, and the walls and ceilings look perfectly normal. However, this doesn't make sense once we place people inside. If this were to be a normal room, then the woman in front would have to be almost twice as tall as the man in the back. And in fact, this is not a standard room. The floor is not level, and this is not a regular checkerboard pattern. The floor is elevated at the left side of the room, and the room extends further back on the left side as well. And this handcrafted room layout is specifically designed to trick the priors in our brains. With this example, I wanted to show that with a single image, we don't only have scale, but also structure ambiguities, where by structure, I'm referring to the actual shape of the room. Sina and Adelson back in 1993 showed that this planar drawing is geometrically consistent with infinitely many 3D structures. Fortunately, for 3D human reconstruction, art becomes much easier. So this is because for humans, we have models and strong priors about their shape, and this helps us resolve some of these ambiguities. To make this less abstract, let's see some examples that illustrate reconstruction ambiguities in the context of human pose estimation. First, we often have truncations. Truncations happen when part of the body is not observed at all in the image. In this particular image, we don't have a way to tell where the legs of the person are. Might also have occlusions. These occlusions can be from other people, objects, the environment, or even self-occlusions. Here, the left hand of the person in the center is occluded by the right player. The most common ambiguities that are almost always present, though, are depth ambiguities. Look at this image with the circle. Since we only observe the 2D projection of the different body parts, it's hard to infer if the right wrist or the right elbow is closer to the camera. To give you a better sense of the difficulty of the problem, let's consider the last case, where we only have depth ambiguities. Conceptually, this is the easiest of the three. And let us also assume we have access to a body model like the ones I showed before. So this figure is from the seminal work of Li and Chen from 1985. What this shows is that given a body model with kinematic chain structure, the problem of lifting 2D landmarks to 3D has an exponential number of plausible solutions in the worst case. This is because for any parent-child joint, there are two configurations that achieve the same projection. To illustrate this, here's an example with two different bodies that explain the image evidence. There are differences both in the body orientation as well as the actual body pose here. So This talk will focus on three important problems in reconstructing 3D bodies from images and how our work attempts to solve them. The first problem is the limited availability of annotated data, and will present a method that attempts to address it. The second problem is about modeling the inherent ambiguities of the reconstruction, and we show that modeling these ambiguities can be really helpful for a series of downstream applications. And last, we'll talk about moving beyond single-person 3D pose estimation and scale our methods to work on scenes with multiple humans. Before diving into the details, I wanted to give you a sneak peek of the level of reconstruction quality we can currently achieve. By the end of this talk, you'll have learned how our methods enable this. So here's me with two of my high school friends during our vacation last summer. And this is the result we get. What you're seeing here is the reconstructed body for each one of us, shown with a different color. And here's an animation of this reconstruction where the camera moves around in space. Notice how we were able to not only recover an accurate per person pose, but also place the people correctly where they should be. So let's now start from the very beginning. How do people solve 3D body reconstruction? The most intuitive way to solve this is with optimization. And in fact, back in the early days, this was how it was done. Here I show some representative examples of pioneering works in this direction. And let me basically explain how this works. So given an image, we can first detect 2D features, such as the silhouette of the person, the body part segmentation, or 2D key point location. And then we cast pose recovery as an optimization problem, where we try to minimize the projection error between the observed evidence and the model output, plus a set of priors on valid poses. Here you can see the optimization process when fitting the simple body model on 2D key points. When the optimization succeeds, as in this case, it tends to have very good image model alignments. Optimization in the context of human pose estimation, though, has several problems. First, it's a non-convex problem that's quite hard to solve. It requires a good initial pose guess to convert to a good solution. Here, I show some examples of the sensitivity of the optimization to the initialization. So the steps that you're seeing here are like different reconstruction results starting from different initial pose guesses. The other problem is that optimization-based reconstruction is typically very slow and definitely not real-time. One more issue is that the output accuracy relies a lot on the quality of the detected features. When these are wrong, it will most likely fail. Notice the leg flipping in the left image. So the key point detector classified the left leg as the right leg and vice versa. So the final reconstruction tries to fit on those key points and it's obviously wrong. Also in the right image, the left hand detection is off. It has the detector has actually detected the left hand on the jacket sleeve and not where it actually is. So the last problem is that fitting on 2D evidence suffers from the known ambiguities of the 3D to 2D mapping. On the left image, you can see the final body orientation is flipped, while the optimization is still able to achieve a very low projection error. On the other image, the right angle of the person reprojects to the correct location, but the depth is obviously wrong. We know that the right leg should be in front of the left leg and not how this is depicted in the reconstruction. These issues eventually shifted the interest to regression methods. Here, the input is an image containing a person, and this image is fed into a neural net that predicts the body model parameters directly. One of the first approaches to attempt this directly from images is HMR from Kanazawa et al. So the standard way of training such a method would be to collect a dataset with model parameter annotations and supervise the network output directly. However, such data is generally not available. What kind of data do we have? On the left, we can see some datasets with 3D annotations. These are typically captured in studio environments and use special equipment or multiple cameras. You can imagine that if we just use those for training, our model will not generalize in challenging new scenes. On the right, we have popular datasets like Coco that have no 3D but include 2D key point annotations. To maximize the performance, the key here is to use all available annotations. Previous methods consider using the 2D key points, and supervise the network with a reprojection loss during training. However, this is suboptimal since the reprojection loss is a weak form of supervision. So can we do better? The answer is yes. We can leverage optimization. When the optimization succeeds, it tends to have really good image model alignment. To succeed though, it requires good initialization. We can initialize the model fitting process with the output of a regression network. A good initialization will encourage the optimization to converge to a good solution. The two paradigms can be used in a tight collaboration to improve neural network training. So how is this possible? So first, optimization methods provide image-aligned results that can supervise the regression network. And this supervision happens directly at the model level. Second, a properly trained regression network can provide good initialization for the optimization and encourage it to converge to a good solution. These observations led us to develop our ICCV 2019 paper, SPIN. SPIN stands for Simple Optimization in the Loop. Our key contribution here is the new way we approach the neural network training. We train our network as follows. At each training iteration, we feed an image in a network that predicts the simple model parameters. We then use the regress body to initialize the optimization that fits the model on 2D joints. After this converges, we use the optimization output to supervise the network. And here's another example. The process is the same as before. So given an image, the network predicts the model parameters. These are used as initialization to the fitting routine, and the output is then used to supervise the network. Notice that our approach is an order of magnitude faster than the original simplifier. So let's talk now about the key advantages of SPIN. First, the optimized shape provides direct supervision in the body model parameters, and this is beneficial compared to weaker reprojection losses. Second, our approach is self-improving. So better network estimates can lead the optimization to better solutions, and more accurate fits provide better supervision for the network. One way I like to view this procedure is through the lens of the teacher-student framework. So here the optimization plays the role of the teacher and the network the role of the student. But there's a key change happening. The teacher is not static, since the student probes the teacher to improve during training. The probing comes in the form of better initialization. Now, let me show you some results from the 3dBW dataset. Please note that these are single frame predictions, and we did not apply any form of post-processing. On the quantitative side, our model outperformed previous methods that were trained on the same or similar datasets. And at this point, I'd like to mention that we're very happy to see SPIN being widely adopted in the community and forming the base for new exciting research works. Here I show some of them. So Vibe from CVPR 2020, there's a temporal pose regression network on top of SPIN. Touch from CVPR 2021 uses our model and training procedure to train a regressor on data of people mimicking poses. Coulon et al. From CVPR 2020 use optimization on top of regression to generate annotations for a hand pose regression. And EFT from 3DB 2021 fine-tunes a network at test time to generate pose annotations. It's worth also mentioning here that our in-the-loop optimization is not limited to 3D human pose estimation and has a lot of unexplored potential. It can be applied to much more general settings where obtaining annotations is very hard. Potential applications include general 3D reconstruction, SLAM, or even tracking. So given some initial network predictions, one could formulate an optimization problem to refine them, and then use the optimization output to supervise the network during training. Similar ideas have been explored, for example, in consistent depth estimation from SIGGRAPH 2020. This work proposed to optimize the weights of a depth prediction network at test time using geometric consistency losses and improve the results significantly compared to the original network. And before moving to the next part, I wanted to very briefly bring up one additional work that deals with the scarcity of annotated data. This is also an ICCV 2019 paper called Text Repose. Here, the main insight is that we can leverage sparsely annotated videos. We do not need annotations for each frame, not even 2D annotations. So how does this work then? Well, it turns out that we can use a texture consistency loss. For any pair of frames, we minimize the texture difference for all mutually visible vertices. And this concludes the first part of the talk. So the key takeaway message here is that we can address the lack of annotations by leveraging a regression optimization collaboration. Let us now shift to the second part. So the second part will focus on the reconstruction ambiguities. We know that 3D pose estimation methods are becoming more and more accurate as more data becomes available and the network architectures improve, of course. However, we need to take into consideration that this problem is very challenging and actually inherently ambiguous. Remember that we need to reconstruct a 3D shape after being projected in 2D, so we have already lost some information. Most neural network models like HMR are only regressing a single output. This is convenient and helps with the evaluation and comparison among different models. However, there is some uncertainty in the reconstruction which we did not consider. For example, if there's a truncation, we'd like our model to provide more than one possible outputs. Hopefully, this should have different proposals for the part of the body that's outside the image. But this is something that's not really happening though with most state-of-the-art models. In our ICP 2021 work called ProHMR, we advocate that we should rethink the way we are doing human mesh recovery. Instead of regressing a single estimate, as I like to say, we propose to embrace the reconstruction ambiguity and recast the problem as learning a mapping from the input image to a distribution of plausible poses. We call this approach ProHMR for probabilistic HMR. So the network outputs a probability distribution from which we can sample different poses, each with different likelihood that indicates how likely they are to correspond to the input image. I would like to clarify here that the observation about the uncertainty in the reconstruction is not a new insight. There's an intuition that exists in many previous works, but it was always hard to operationalize this insight. And in fact, many recent works have actually attempted to solve this task. Many of these solutions, at least at the time we started working on the problem, were only considering very simplistic distributions for the modeling part. Others used ensemble-like methods with multiple hypotheses instead of one. So I believe that compared to some of these works, we have a more elegant formulation that can give a very expressive distribution of poses. But more importantly though, we believe that a crucial difference is our focus on the different downstream tasks where this model can be used. By treating our trained probabilistic model as a conditional distribution, we can use it in many downstream applications to combine information from different sources. So we can consolidate information from different viewpoints or from images and 2D key point detections. We'll talk about each of those applications in detail later in the talk. But anyway, let us see our ProHMR approach in more detail. The basic architecture is the same as before. Given an input image, our image encoder regresses a feature vector C, which is used as the condition information of the probabilistic model. To learn the probability distribution of poses given the input image, we use conditional normalizing flows. With conditional normalizing flows, we learn a bijection that maps the standard multivariate Gaussian to the target output distribution of poses, and this mapping is parameterized by the image features C. This bijection is implemented as a composition of several simple invertible transformations whose inverse and Jacobian determinant are easy to compute. So effectively, we start from a normal-based distribution for Z, and with a series of invertible transformations, we can model more complex distributions for the output, here theta, the body pose. In parallel, it is also decoded to the shape parameter beta and the camera P. We don't use the same probabilistic modeling for the body shape parameters because of the lack of sufficient annotations for body shape. Instead, we simply use a deterministic mapping here. We give some more details about the flow model. We effectively learn a mapping which allows for two processing directions. Depending on the desired function, we can perform both sampling from the output distribution and fast likelihood computation. For sampling, we'll sample a point from the standard Gaussian and transform it to a body pose using the learned mapping. For likelihood evaluation of a given 3D pose, we apply the inverse mapping. Both of these mappings are conditioned on the image features C. Our choice also another useful property. The mode of the output distribution is a transformation of z equals 0. This is very useful as it allows us to use our model as a typical regression. Every time we want to make a single prediction without any additional context, it makes sense to return the mode. And let's now talk about how we can train our model. To do that, we divide our data into two subclasses, the examples with and the examples without 3D annotations. For examples with 3D annotations, in the usual normalizing flow fashion, we maximize the log likelihood of the ground truth annotations under the model, or equivalently, minimize the negative log likelihood. To be able to utilize 2D datasets within our framework, we propose to minimize the expectation of the 2D errors. We might not have ground truth annotations to maximize the conditional probability, but we can still constrain the form of the output distribution. We do so by forcing the output samples to have an average lower projection error and lie on the manifold of valid poses. As in the case of VEEs, we approximate the expectation by drawing a single sample from the posterior. We mentioned here that our goal is to use our model not only as a generative model, but also as a predictive model. Thus, we propose to exploit the property that for each segment, the mode of the output distribution is the transformation of z equals 0. We do that by explicitly supervising the mode with all the available annotations, as we would do in a standard regression framework. Since we can get the mode of distribution, or in other words, the most likely pose given the image, by simply transforming z equals 0, we can easily compare our model with previous state-of-the-art methods that regress one 3D pose. We evaluate on different benchmarks, and we perform comparable or better than the related regression methods. And here I also show some qualitative results. I present both the mode and different samples. You can see the variety for the different samples, particularly when it comes to the different depths for the body parts, which is the main cause of ambiguity here. There are not like a lot of occlusions or truncations. And next, I'm very excited to show you our results on model fitting. That is, like, model fitting is one of the most exciting applications of our method, in my opinion. And this is typically a very hard problem. Our model provides a new way of approaching it, and this can, in theory and in practice, eliminate most of the common problems we face with the optimization methods. Remember that in model fitting, we form an objective that consists of a data term and a set of priors. The data term measures the reprojection error of the model joins. The priors are statistical priors on pose and shape and possible geometry that encourage the validity of the final reconstructions. In traditional model fitting, the objective is purely driven by the 2D key point locations, and it disregards rich information contained in the image. In spin, we partially address this issue by using a regression network, and this regression network provided a good initialization for the optimization. This helped the fitting converge to a better minimum. However, the optimization method we used, Simplify, does not incorporate explicit image-specific priors. This means that there is nothing preventing the pose to deviate arbitrarily far from the set of plausible poses for the given image that we have. To frame our contribution as concisely as possible, we propose to replace the generic 3D priors with an explicit pose prior conditioned on the input image. Let us see some results first, and then we can talk about the rest of the details. Take a look at this particular image, for example. Here, I show two action candidates. Can you guess which one is closer to the actual solution? I would say probably the right one, but how do I know? Well, there are some depth cues in the image that we as humans are trained to recognize. These cues are exactly what our image-based prior attempts to capture here. And spoiler alert, the result on the left is with a traditional fitting, whereas the one on the right is with our image-based prior. So let me show you qualitatively how to get to these two solutions. So we have an image with its open pose detections that are overlaid on top of the image. The first row shows the fitting process with our image-based prior, whereas the last row shows the fitting process without in both cases is to match the open pose to decay point detections. The last column shows the reconstruction from a side viewpoint. Now, I will play a short animation of the optimization, starting from the regression output, which is the same in both cases, until convergence. You can immediately observe that the reconstructions look similar on the frontal view. Indeed, both of them manage to achieve a very low projection error. However, if we look at the side view, we can clearly see that the optimization result without our image-based prior starts to deviate a lot from the original prediction. And in the end, it yields a much less accurate result. At the same time, fitting with our image-based prior speeds up convergence as well. And here's another example. Again, the first row refers to fitting with our image-based prior, whereas the second row with the generic 3D prior. What is this new prior term then that we used? Well, it's simply the negative log likelihood of the regressed distribution that we can compute analytically, because we are modeling it with normalizing flows. And here are some more results for the fitting. So this figure shows a three-way comparison. First, there is the pro-HMR regression output with the pink color. And then in the middle, you can see the optimization result with our learned distribution. And last, with a gray, we show the results of the vanilla key point fitting. You can see that the regression is close to the actual result, but doesn't always align very well with the image. The vanilla key point fitting often aligns well, but it fails if key points are not detected. A good example of this is the example of the last row, where we don't have any key point detections for the right leg. And at the same time, the detections for the left leg have very low confidence, so they are practically ignored during fitting. And the fitting with our image-based prior managed to remain much more faithful to the image evidence compared to the vanilla key point fitting. So our fitting with our learned distribution combines the benefit of both regression and optimization. We get a result that aligns well with the image, while also using image-based information to eliminate the ambiguities that are associated with fitting on 2D key points alone. Also, we evaluate this fitting with comparable baselines. Here we get very strong results as well. For the key point targets, we use open pose detections. Some of these benchmarks are more saturated, but we're still able to get quantitative improvements. The first baseline, spin plus simplify, refers to fitting on top of the spin prediction, which is essentially equivalent to the vanilla fitting results we showed before. EFT is a related work that recasts body model fitting as a test time optimization. And both EFT and simplify suffer from drifting issues because there is no explicit image-based prior that can constrain the output space here. So given enough steps, there is no guarantee that the output will not deviate arbitrarily far from the initial guess. And here I have some more cool results for the fitting. These are from some online fitness instruction videos with fast-paced motion. Again, all these results are frame-by-frame fitting, yet they look pretty smooth. The final application we investigated in the paper was multi-view fusion. This means that we have access to multiple views of the same pose, and we want to consolidate information to find the most likely. So here you see 4 views of a subject. The second column shows the initial predictions, which is the mode of each view. In the third column, we show these in a common reference frame. Notice that the right-hand position in the first image is occluded, and the reconstructed pose is not very accurate. The last column shows the refined results obtained using optimization. What we're actually optimizing here for is the sum of the negative log likelihoods in each view, plus a cross-view consistency term. In terms of quantitative results, the multi-view fusion managed to improve the pose metrics compared to single view and simpler multi-view baselines. So in ProHMR, we discussed quite a few possible applications of our probabilistic modeling. We talked about being able to regress 3D bodies, fit bodies on 2D key points, and refine our predictions when we have access to multiple views. However, our model is not limited to just those that we explored in the paper. You can imagine that the general framework can be very useful for effectively fusing information from different input modalities like RGB plus depth, point clouds, or even external sensors like markers or IMUs. Very often, the sensor outputs are noisy, so pose estimation could benefit from a more holistic reason. And to sum up, the key takeaway message for this second part of the talk is that modeling the ambiguities is helpful. Our model can do what a regular regression model does, and at the same time is useful for solving additional downstream tasks. So what we've talked about this far has been about reconstructing people one at a time, independently from one another. Humans, however, are not isolated entities. They live in a world where they interact with other humans and their environment. Here, we will present our work that we published at CVPR 2020 and focus on predicting a coherent reconstruction of humans in challenging real-world scenes. As a starting point, we have the approaches for human mesh recovery we discussed before. These works predict the parameters of a body model and tend to work pretty well for a variety of images, as you can obviously see here. They're intended for a single human, though, and they take as input an image of a single person. The person needs to be centered, and we need to crop the image around the person. But what happens when we look at a larger scene? Our real images rarely include a single person. We typically have multiple people interacting with each other or occluding each other. How should we treat these cases? The straightforward solution would follow the principles of top-down processing. We first detect a bounding box for each person in the image. And this should be easy and effective to do with the recent detection systems. And then we process each bounding box independently with a network for human mesh recovery. Surprisingly, this doesn't look too bad, right? We get a reasonable pose for each person, so we should be able to combine them and get a result. Well, a result that is incorrect. Let us also take a look from the top view. Yeah, the combined result is incorrect, or actually incoherent. Perceptually, what we care more about here is the coherency of the holistic result. As we advance towards holistic scene understanding, we want to be able to perceive not only the local pose of each person, but also the relative positions, their proximity, their interactions, the potential contact with other people. We didn't get these details correct here. The independent pose of each person is reasonable, but if we compose the results together, the output is not accurate. So what have we been missing here then? The answer is we need to look at the holistic result. Composing results is nice, but you often need to be smarter about it. So instead, a coherent result would look something like that. And yet, this result is our goal here. Ideally, we want an approach that takes a single image and regresses the mesh for each person in the image. And as we discussed, the final reconstruction should be coherent. The relative depths of people should be correct. The relative poses should be reasonable. There should be no overlap of the meshes on the 3D space. So our proposed approach takes as input an image and feeds it to a typical RCNN network. Using a shared feature map, we first detect bounding boxes for the people in the image, and then we regress the simple parameters for each bounding box. So this part, in a way, follows the typical top-down regression paradigm. What we need to predict here is an accurate placement of the people in the 3D scene. As we saw in some examples before, we can predict bodies that reproject correctly on the 2D key points, but the relative depths are clearly wrong. And this produces an incoherent scene. Our goal here is to exploit geometric constraints and the data that we have to encourage the network to predict more coherent scenes. For this reason, we incorporate two novel geometric losses. There is an interpenetration loss that's responsible for collision avoidance. We don't want people to overlap each other in the 3D space. This doesn't require any extra annotations, and we can use the network output for self-supervision. And there is also a depth ordering aware loss that makes the rendering of the reconstructed people consistent with the instant segmentation masks. The intuition here is the following. Segmentation masks give cues about occlusions. If we know that one person is occluding part of another person, then this body part has to be closer to the camera than the occluded body part of the other person. These losses are applied during training, encouraging the network to make coherent predictions. At test time, we rely on what the network has learned and make the predictions in a feed-forward manner. I want to mention here that we're not the first to attempt to solve this problem of model-based pose estimation. There are two works from Zanfir et al. From CVPR 2018 and Europe 2018. And the first used scene constraints in an optimization framework, whereas the second used a bottom-up regression approach by first detecting body joints, followed by grouping and then pose estimation. Let us now look in more detail how these losses work. Our first loss is an interpenetration loss. Since we use a feed-forward regressor, there is no guarantee that the predicted meshes will not penetrate each other. And in fact, very often we have this collision problem with our predictions. To avoid this, we need to penalize the vertices of mesh 1 that penetrate mesh 2 and vice versa. Ideally, vertices that penetrate the mesh far from the surface should also be penalized more heavily. An efficient way to compute the penalty is to generate the distance field of each mesh. The value of this distance field depends on the distance from the mesh surface. On and outside the surface, we get value 0, while the value increases as we move further inside the mesh. Then, the penalty for each vertex can be computed efficiently based on the distance field value of the neighboring meshes. This is done by using trilinear interpolation on the distance volumes. So, this loss is effective at avoiding the penetrations, while it also needs no annotations. This is just a property we enforce at training time because we know that it should always hold. We don't need access to some sort of explicit annotations to supervise the network. Besides the interpenetration loss, we also use a depth ordering aware loss. What we do is, after reconstructing the full scene, we render the holistic result on the image, keeping track of the instance IDs for each mesh. So these are silhouettes with the identities of each person. And then we compare the result of the holistic rendering with the instant segmentation masks of the scene. These masks are available in large-scale datasets like Coho, so they're easy to get. We aim to fix errors in depth ordering of the people in the scene by enforcing the consistency between the holistic rendering and the instant segmentation. If a pixel is annotated to belong to person 1, but we render it on the silhouette of person 2, it means that we need to put person 1 closer to the camera in the reconstruction and push person 2 further away. So this will improve the depth ordering of the people in the scene. Also, what is interesting here is that we only use 2D annotations. In fact, we only use simple instant segmentation masks, yet we're able to improve the 3D reconstruction by eliminating some of the ambiguities. So we get better 3D without extra 3D annotations. This is very important considering that 3D annotations are not available in general. Also, for some of the more technical details, to make this loss more efficient, we use some tricks to make sure it's applied to the shapes of both people involved here. Differentiable rendering losses have the issue of propagating gradients only on visible vertices, making them less effective than expected. We also observe this behavior and we follow a more balanced approach. We use a formulation where we render a depth mask for both the visible and the occluded person independently. So we consider the depths for both people, and thus gradients are propagated to the occluded as well, making training more stable in practice. Essentially, we find the pixel where there's a disagreement between the rendered scene and the instant segmentation, and we apply the depth ordering loss on those pixels. If we do not render the shape for both people, then what happens is that the only way to resolve the disagreement is by pushing the closest person further from the camera, and this sets a bias in the training process. And with these novel losses, we were able to improve the typical top-down regression approaches. Here, we compare with a baseline that's trained without our losses and with our food model. The baseline results are on the left, and the results of our full model on the right. You can see the improvements in avoiding depth ordering errors and collisions. In this work, our main contributions were the geometric losses we used to improve the multi-person pose estimation. We're very excited to see that the vision community has found their ideas and implementations valuable and has used them in subsequent works. One example is the work of Zhang et al. From ECCV 2020 that focuses on joint human object reconstruction and incorporates our depth ordering aware loss in their optimization framework. Ferraro et al. Also used our depth ordering loss to train a multi-person pose estimation network with transformers. Our STF-based collision loss is also used in the two recent hand object reconstruction works by Cao et al. And Hasson et al. That incorporated into their optimization framework. This shows that our geometric losses can be useful beyond just body pose estimation, and it can be used to solve a variety of related 3D problems. So up until this point, we talked about my work on regression optimization collaboration, modeling reconstruction ambiguities, and scaling our methods for more than one people. Is that all though? Did we solve all problems in 3D human pose estimation? Of course not. We have a lot of areas that still remain unexplored. However, we have developed a very powerful toolbox that will allow us to work on problems that a few years ago might have looked unsolvable. What should we do next then? Let's revisit this photo of me and my friends that I showed you earlier. Now, I'm going to put together all the tools that I've developed so far and do my best to reconstruct this scene. And here's the reconstruction. To achieve this result, I used the model fitting method of Freud's MR, which I augmented with the collision and depth ordering aware losses. By moving the camera around in space, you can see that we're not only able to recover an accurate per person pose, but also place the people correctly where they should be. But something is missing though. We see that me and my friends are obviously sitting on chairs. People don't just float around in empty space. We're also sitting next to a table where we have placed most of our stuff. Our environment defines a set of affordances that dictate how we live and move inside. Conversely, humans also constrain their environment. Typically, reconstructing general scenes is harder than reconstructing humans, and an accurate human reconstruction should give us a strong signal about their surroundings. We've already done some work on multi-person modeling, but our work didn't go beyond basic geometric constraints, such as collision avoidance, for example. Human interactions are much more complex than modeling simple spatial proximities, though. Oftentimes, there's additional semantic context involved, and to take reconstruction and scene understanding to the next level, we need to take this into account. What do I mean by context, though? So chairs are an example of an object that we interact with in specific ways. People normally sit on them as we saw in the image on the left. Sure, standing on a chair is possible, but people normally won't do it, especially on chairs with wheels, because this is extra dangerous. And same for knives. We grab them from the handle, and the sharp edge is facing away from our thumb. Or for a glass of water. When it's full, we'll always grab it this way. We never hold it upside down. Well, unless we're trying to pull off this famous trick with the paper on the bottom. I've been thinking a lot lately about the problem of modeling humans jointly with their environment, both at the level of reconstructing people in scenes and at a finer level where we model hand-object interactions. The two problems have a lot of applications in augmented and virtual reality. The key here, in my opinion, is to reason about humans and their environment jointly. We need to incorporate semantics and move beyond purely geometric methods. Scene understanding and context are more important. And to take this one step further, semantic context is useful for tasks way beyond the ones I described. One such task is reasoning about the future. Look at this snapshot from an NBA game. You can see Chris Paul holding the ball in his hands. So what is going to happen next? Is he going to dribble, pass the ball, shoot? Well, neither of these. He faked a shot, then faked a pass, and finally went for the shot. Short-term motion prediction is all about modeling the biomechanics of human bodies. Predicting long-term in the future, more than a couple of seconds, requires reasoning about intent and the context we're currently in. Clearly, there are cues in the image, but extracting them can be hard, but it would definitely help if we could reason at a higher level. For instance, Chris Paul is known to be a very good ball handler, and the defender who is approaching him is much taller than him. So it makes sense for Chris Paul to try and fake the shot. Otherwise, if he goes for it, there's a good chance that it will be blocked. This is an example of semantic context and how it can be helpful for predicting the future. And this is another example that shows why predicting human behavior in the future is important. So consider the case of self-driving cars. Autonomous city driving is much more challenging than driving on a highway. The computer on the car should be capable of sensing what other cars and pedestrians are about to do. Is this person aware of the traffic around them? Maybe not, because they're looking at their phone. So the car may have to be extra careful here. Will they try to cross the street? If yes, it needs to come to a stop. Otherwise, slamming on the brakes simply because a person is close to the crossing might put other cars in danger of an accident. And one last point I wanted to bring up is that nowadays, wearable devices are becoming extremely popular. One example is smart glasses, but we don't have to constrain ourselves to input only from cameras. We often carry with us our phones and smartwatches. Companies have also developed smart shoes and clothing that can capture and analyze biometric data. And all these different devices can be tightly interconnected. So I believe we can explore all these additional modalities to reason about the world. And the key here is we want to place humans at the center of the experience. We want to reason about the world through the lens of us, humans, and actually do so in a personalized way. Not every human perceives the world in the same way. And this is influenced a lot by our diverse experience and backgrounds. We want to build systems that will continuously adapt to our behavior and serve our needs in an optimal way. This is a full list of publications I authored during my PhD. Unfortunately, we did not have time to talk about all of them. Aside from work on humans, we've also done work on modeling the 3D shape of other articulated objects like birds. I also want to mention here that we have open sourced the code for all our papers on GitHub. I encourage you to check them if you're interested. And last, this is a collection of my collaborators in my publications. I'm really, really grateful for having worked with each one of them. Thank you. So I guess we can take questions. There are some questions in the chat already. So I can start to answer those first. So the first question by Edward is, does model and pose get optimized simultaneously? So the body model that we use is simple. So what we're optimizing simultaneously is for the shape of the person and the pose. Of course, there are some tricks involved here. I think it's better to talk about them offline, because it can be rather technical. So sometimes it's convenient to first estimate the translation of the person and then start optimizing the body pose to make sure you don't get improbable poses, because it might try to snap to the key points very early in the process, and it can get stuck in some local optimum. So the second question, Junya, is how long does it take to get reconstruction from one image using optimization versus regression? So the regression methods run at 33 FPS. For my spin paper, we've measured it. It's on a 2080 Ti, it takes about 30 milliseconds per image. So for the optimization, with the current deep learning frameworks like Pytorch, it might take, so if you start from a visualization and only do one stage, it can take around say 5 seconds. But with the original implementation where you have to do multiple stages to account for the fact that you don't have a good visualization, this can take for up to a minute to converge. And the other question is, why do I use conditional normalizing flows instead of conditional VAEs? One reason we did that basically is that in VAEs, you don't you don't get exact likelihood that you can optimize for. Oftentimes you can, like what people have done is search in the latent space and have a quadratic, like an L2 penalty on the latent, but this is not really equivalent to the likelihood, as you know from the way we train VEs. So the evidence lower bound is the sum of these like KL divergences plus the reconstruction loss, which is basically unknown. So normalizing flows have the advantage of like being able to sample from distribution and actually evaluate the likelihood of a particular sample in a straightforward way. Okay, these are.
Sorry, why is it important to evaluate the likelihood of your estimation?
Sorry, can you repeat that?
Yeah, sorry. I was asking, why is it important to evaluate the log likelihood of your predictions?
So why is this important? 1 second, let me get to the relevant slide here. It's actually this slide here. So actually, we have this term that the first term EJ is the projection loss, and then we need to, so we use it as a regularizer in the optimization actually. So you can view it as kind of maximum a posteriori estimation, where you have like one likelihood that comes from the observation, which is the key points, and the other likelihood term comes from the conditional distribution our model regresses. So yeah, so we explicitly use this likelihood term in the optimization framework.
Okay, thanks. I have another question, but like if other people have questions, you guys should go first.
Go for it. Go for it.
Oh, okay. So, so I'm working on like a project that has like a component of 3D reconstruction, and then I was just wondering, what's your perspective on 3D hand reconstruction versus human body reconstruction? Like, what are the difficulties and challenges? And then like.
Oh, okay, this is a kind of similar problem. So there are the amount of ambiguity in the hand estimation. I would say it's from my experience, because I've also worked on this problem for hands, is slightly smaller. So compared to bodies, because you don't get that much pose variation. But for hands, you have other issues, like often a lot of motion blur. You have a lot of occlusions. Imagine like you're grabbing a mug or like objects like that. So you often don't see a large part of the hand. So it has its own set of difficulties, but the methods that work for human bodies definitely can transfer to hands and vice versa. So if you're using, like, for example, the Mano model, which is a parametric body model for hands, then pretty much you can apply, like take our methods out of the box and apply them to your problem, given that you have the data to train that.
So you're saying that we can just use your pro HMR method, but just change the parameters to Mano parameters?
Yes, exactly. Yes, exactly. Yes.
I see. But like, this is not like there's no available model off the shelf we can use. We have to train this by ourselves.
Yes, you have to train. So there are datasets for that. If you want more details, you can email me, so I can provide you a list of datasets that you can use to train such a model. Yeah, if you have any questions, just email me and I will send you a full list for that, to where to start from. And I have the code public on GitHub, so you can just swap out the body model with Mano and train it yourself.
Yeah. And like, do you expect the performance of like 3D reconstruction in the well dataset, for example, like something datasets or Epic Kitchens, to be like as good as what you showed us today for 3D?
Yeah, you should expect, if you like, yes, you should expect this a similar level of quality, because the other advantage with hand is if you train on image crops, it actually generalizes pretty well in challenging videos whereas humans, you have a lot more background variation compared to hands. So for hands in this case, it's slightly easier, but of course you have issues like motion blur or lower resolution and things like that. In some videos, hands can be just like 10 pixels, 20 pixels. So it's really hard to make anything out of it there.
I see. But you mean like using your method, not like any other off-the-shelf method, right?
I mean, you can definitely try to use like HMR or something like that instead of our probabilistic method, and this should also work. So if you want more details, you can email me.
Thank you. I'll do that. There's another question, so I'm gonna stop talking.
I think I saw Rosina raised her hand.
Yes, I did.
Hello.
I did. My question is speed. How fast can you do this? Namely, what I'm interested in, imagine two people in different location and they want to dance together, which I tried 15 years ago or something like that. And of course, the network was not fast enough, but now we have faster network. So can you deal with this?
Yes, actually, so the pure regression, where if you regress and don't optimize, this runs in real time. It's like, actually, it's last time I checked, it was 33 FPS. So it's actually real time. For the
That's
optimization.
good. That's real time. Yeah, good, good. So you can reconstruct in real time motion so that people can synchronize, correct?
Yes, yes, we can do it in real time.
Okay, so you should have a little demonstration on that. I think that would be fascinating. Imagine that now, the artists are in really trouble. And they are struggling, and this would allow them, even if they are not in the same location, perform.
Exactly, yes, that's a really nice application. Actually, I think we're going to prepare a demo for ICRA and show some of these results to people.
Good. Make sure. Yeah, good. Excellent. Okay.
Thanks.
Thank you.